Hi, I'm Jordan Holmes, and this is my video of the Hardy-Weinberg lab. In this lab, we will learn about the Hardy-Weinberg equilibrium, the effects of natural selection on the changes in allele frequencies, how to determine allele frequencies using the Hardy-Weinberg equilibrium, and how to calculate those frequencies in the genotypes, and how natural selection can cause microevolution and the changes in allele frequencies. So for a population to be in Hardy-Weinberg equilibrium, that means the allele frequencies do not change over time. And the conditions for Hardy-Weinberg are that the breeding population must be large, mating must be random, there's no mutations occurring to the alleles, there's no migration, and there is no natural selection occurring. When talking about Hardy-Weinberg, the recessive allele is represented by a lowercase letter, and the dominant allele is represented by a capital letter. In Hardy-Weinberg, the letter P represents the dominant allele, and the letter Q represents the recessive allele, and the frequency of the dominant allele plus the frequency of the recessive allele should equal 1. And when you find the frequency of the alleles, you typically display them in a table, such as this one, and where P is the dominant allele, Q is the recessive allele. P squared represents the frequency of individuals with the homozygous dominant genotype, and 2pq represents the frequency of heterozygous individuals in the population, and q squared represents the frequency of homozygous recessive individuals. And once you fill in this chart, you should find that p squared plus 2pq plus q squared equals 1. The materials necessary to perform the Hardy-Weinberg lab include the allele cards and a coin. So when we do the lab, we have one parent, which is represented by the cards on the table, and one parent, which is the cards in your hand, and both parents in the beginning of case 1 are heterozygous individuals. So what you're going to do for this lab, you turn over one card from your hand and one card from the other cards on the table, and this represents your offspring. So once you've found your first offspring from selecting the cards, this is the genotype of the offspring that will be the cards in your hand. And so then you take the cards and you put them back and you reshuffle them all. And then you'll do it again to get the second offspring, which will be the genotype of the cards on the table. So after doing this, I found that both of the offspring were heterozygous, so when I reset the cards, they'll be the same as they were in the beginning because they were both heterozygous to begin with. In case 2 of the Hardy-Weinberg lab, the homozygous recessive allele was lethal, so that means they do not reproduce, and you must keep trying again until you come up with a genotype that can survive. In case 3 of this lab, the homozygous recessive individuals do not survive, and the homozygous dominant individuals only survive if the coin toss comes out tails. So if you get one of these homozygous individuals, you must keep trying until you produce 2 viable offspring. So in case 1, the expected results for 2 heterozygote individuals would be 0.5 frequency for the dominant allele, 0.5 for the recessive allele, and a 0.25 frequency for the homozygous dominant individuals, a 0.5 frequency for the heterozygous individuals, and a 0.25 frequency for the homozygous recessive individuals. And in case 2 and 3, where the homozygous recessive individuals never survive, the frequency of the recessive allele will be drastically reduced. Potential sources of error in this lab include resetting the cards wrong, such as including 3 dominant alleles instead of 2 and 2 when it's a heterozygous offspring, or forgetting to reset the cards altogether, which reduces the number of alleles in the population, which should always be 4. Thanks for watching. I hope you learned a lot about the Hardy-Weinberg equilibrium.